Okay, looks like we're recording again. Sorry for the unexpected interruption there. Okay, so here's where we were. We were computing this stretching factor here, and we made the observation that it comes from taking these partial derivatives, right? And then we take the cross product of those partial derivatives. And then we take the magnitude of that cross product of those partial derivatives. So just a bunch of, plug and chug calculation here. And we end up with, as our stretching factor, this function of u and v. Okay, so plugging in. Recall, we were computing a mass. Mass is a surface integral of surface density. Mass per unit area. Computing that density, well, that's just a matter of plugging in the parameterization, right? Density is a function of position. Position is a function of u and v per that parameterization that we came up with. Right, from the previous page, let me just remind you. There's the parameterization that we came up with. So plug that in. The stretching factor, you'll see right there, the stretching factor that we just computed right there. And now we have as promised, we have a plain old double integral. And this can be computed by, methods from earlier in this chapter. Because the domain here is nice. The domain is just whatever the pullback domain was. Let's remind ourselves what that was. We were looking at the graph parameterization. So the domain was what part of the graph we're interested in. We're looking at the part that's sitting over this unit disk in the xy plane. So that's our domain for our parameterization, and thus our domain for this interval, the pullback interval. Everybody good? Okay, again, there's another example that I'm going to let you all read. This one's kind of fun. Just very quickly, we have a minute. This question speculates that, there's an aquarium and there's fish around, right? And that you have one of these underwater viewing stations where, I don't know if y'all been to an aquarium or where they have, real big fish tanks, right? So sometimes I'll have either a dome where you can get up underneath and you can kind of put your head in the dome and you can kind of look around and it's like you're inside at the bottom of the aquarium. It's pretty neat. Sometimes they have a little tunnel that you can climb through or whatever. Okay, how much force is there on the surface of this dome? There's a lot of force, right? Because there's a lot of water pressure. Depending on how deep, at a particular point, the amount of water pressure there is at a particular point depends on how deep it is. So at this point on the surface, there's a lot of pressure there. Pressure times area gives you a force. Well, down here on this little piece, there's more pressure per unit area. Up here near the top, there's less pressure per unit area. Okay? So the amount of pressure, the amount of force per unit area, I think I misspoke a minute. Amount of force per unit area depends on where you are. And so if you want to compute the total force, it's kind of something that you're going to have to add up over the entire surface. Okay, details in the exercise, and I'll let y'all read that. Okay. All right, and of course more exercises. I do note, by the way, that the section on scalar surface integrals is modeled very closely after the section on scalar line integrals. Both the surface integrals and line integrals address analogous questions. It's just one's two-dimensional and one's one-dimensional. And in both cases, we have dimensionally awkward domains. In both cases, we view them as images. In both cases, we do pullbacks through parameterizations. In both cases, there is a formula for the stretching factor that came from looking at the derivative transformation. And in both cases, I get a formula that I can plug and chug into. So it's very mechanical process kind of stuff. Okay. All right, so now we're going to talk about a whole completely different kind of integral. Starting here and going forward, kind of for the rest of the course, we're going to be interested in different kinds of integrals. All the integrals we've seen up to now are scalar integrals. The integrand was a scalar. The integrand was like a density or a concentration or something. It's a scalar valued thing where the ultimate question that we're trying to answer is a scalar quantity like mass or moment of inertia, something like that. Okay. So there is a completely different category of question that can be considered with Riemann sums. The integrand is a totally different critter. Something called a vector field. So before I can tell you about these new kinds of integrals, I have to tell you what a vector field is. And it's ultimately not that big of a deal, but nevertheless it's something we have to talk about. So I'm going to start off with some reminders of things that we represent with vectors. So forces. We represent forces by vectors. Right? And if I talk about the amount of force that there is on this pen right here, then I'm talking about a vector. The force on this pen sitting in this location is it's a vector. There's a direction and there's a magnitude, namely how much this is weighing. So, right, so that's a force, but specifically that's a force that's being applied at a given point. We focused our attention on a single point. The idea of a force field is that it says, well, let's think about how this force applies at various different locations. So let's talk about gravity. This is what a gravitational field looks like. Let's say here's the Earth. Right? Well, if you're there, there's a certain amount of force. If you're here, that's a different location. The force points in a different direction. Right? If you're further away, okay, I think my arm touched the little thing there. Okay, all right, that's probably what happened. Further away, then the magnitude is smaller. Right? But the point is, different points, there's different corresponding forces. So, a single one of these things, like if I look just at that, then I could call that a vector. Right? The vector field is all of these vectors together. How the associated vector associated to a point depends on position. That's called the vector field. So everyone's heard of a gravitational field. A gravitational field is just a vector field giving you gravitational force as a function of location. Okay. By the way, electric fields look pretty much the same. Okay. Now here's a completely different physics example. The flows of fluids. If you have a fluid flowing through a pipe, and we've talked about this kind of an application. Here's the pipe, and we've got fluid flowing through it. So, here at that point, there's a certain velocity. At that point, there's a different velocity. At this point, there's a different velocity. Velocity depends on where you are. Well, if you think about it, this is in fact a vector field. Same deal. For any given location, there is a corresponding vector. Now here the vector doesn't represent a force. Here the vector represents a fluid velocity, not to be confused with a force. Right? Nevertheless, we have the same kind of a picture. We have the same little mathematical construction. If you give me a point, then there's a corresponding vector. So it's still a vector field. It's just a vector field that comes from a different physical example. So vector fields that come from the flows of fluids I like to call flow fields, analogous to force fields. Okay, here's another example. This is another kind of a familiar example. We just never didn't think about this at the time, but at the time, earlier in chapter 4, I guess it was, we were talking about real valued functions and how you can compute various derivatives of various kinds of real valued functions. And we talked about the gradient Right? We talked about how the gradient is a vector, and it has certain nice interpretations. Right? The gradient points in the direction of fastest increase. The magnitude of the gradient tells you what is the rate of change with respect to distance in that direction. And it's a useful construction. And it's a vector, but we only considered in that context one location at a time. We'll talk about the gradient, given a real valued function, we talk about at a particular point, at that one point, what's the gradient vector? Only one vector associated to only one point. We weren't thinking about what's the gradient over here, what's the gradient over there. Right? So I'll just make the observation that because the gradient was a vector that we computed at a given point, that means at every point there is a gradient vector. That means at every point there's an associated vector. That's a vector field, right? So situation like this, right? If you let's see, I hope I have this written. Yeah, here we go. For this function here, for that function right there, f of x y equals x squared plus y squared. Easy to compute the gradient. Here it is, 2x comma 2y. Right, again in chapter 4, we wrote down stuff like this. They're easy to compute. Then if you give me a particular point, focus our attention on that one point. At that point, x comma y, I can compute this vector. I'm just making the observation now that if you simply don't focus your attention only on a single point, then what you have, not focusing on a single point, what you have is a formula that gives you a bunch of vectors at a bunch of different points. You have a vector field. Okay. Any questions? Feel free. Yeah, so here I'm actually going to write it down. Whoops. So the way we write this down is that a vector field is a function from Rn to Rn, and all this means is for every input, now what's the input to one of these kinds of functions? The input is an object in Rn that we're interpreting as a point. So for any given point, there is an associated object in Rn that these outputs we're interpreting as vectors. So the inputs we're interpreting as points, the outputs we're interpreting as vectors. So do be careful, by the way, to, don't interpret this as a change of variables function. I mean, you can interpret a function from R2 to R2 as a change of variables function, where there's an input that I view as a point, there's an output that I view as a point. And I view this as a way of relating points over here with points over here. The points being, helping me define a domain consisting of a bunch of points. So we're not going to interpret this way. We're going to interpret like this. Now again, this is just function from R2 to R2, but the input I interpret as a point, and the output from this function is the vector that I associate to that point. So this is like, I don't know, is this the fifth or the sixth different kind of picture that we have to represent a certain kind of a function? Let's count them up. We have graphs, level sets, images. We have this one where we draw the domain over here, the target over here. You might call it, maybe we'll call that the change of variables picture, right? These are all different pictures that we associate to different kinds of functions for different kinds of purposes. This is not any of those things. This is not a graph of this function, right? I have not drawn the domain and the target in separate worlds. This is not a level set, right? It's yet another kind of a picture that I can draw. So it's at least the fifth, and it might be more. I may have forgotten one. Let's say the fifth. Okay. Alrighty. Okay, so Here's some more examples. Here's a vector field. F of x comma y equals 2 comma 1. Now let's take a moment to recognize that this satisfies the rule. For any point x comma y, there is an associated vector, and the formula for how to compute that output vector that I associate to the point x comma y is 2 comma 1. So not much of a computation. In fact, there's no computation. The answer is always 2 comma 1 for every point. So easy. So what does that look like? I mean, how would I represent this geometrically, this vector field? And here it is, up here. This does not quite fit. I'll zoom out. 2 comma 1. So for this point, the value of the vector field is 2 comma 1. And now wait a second, what about for that point? There's a different x comma y, and the value of the vector field still 2 comma 1. And for this point over here, again, same 2 comma 1. And so we get a bunch of vectors, all the same, 2 comma 1 associated at different points. Here's another one. Zoom back in. F of x comma y equals x comma y. So what does that look like? Well, what this says is whatever point you're at, for that point, x comma y, so let's take x comma y thought of as a point. We're going to take that point and interpret what is its associated position vector x comma y, and note that that's what this output is. It's the position, that's the vector x comma y that is the position vector for the point x, y. So that means we get a picture that looks like this. At this point here, there's the position vector for that point. So that is x comma y interpreted as a vector. And of course I need to draw that per the norm with its tail at the point in question. That's how we draw vector fields. So I get that. So for that blue point, we get that green vector. And same game for all these points, right? For that point, we get that vector, aka that vector. And for this point, we get that vector, aka that vector, etc. Yeah, everybody on board? So by the way, what does this mean physically? How would I interpret this physically? A couple different ways you can think about this. Again, there's kind of two primary physical models that I want you to have in your mind when you're thinking about vector fields. One of them is to think of them as forces. What would it look like? I mean, what is the physical scenario by which this represents forces? A force where, when you're a little bit away, then, the forces always point away from the origin. And the further you get away from the origin, the more force there is away from the origin. That's not how gravity works. It's not a gravitational field. It's not an electric field. Electric fields don't work like that either. All right, so you might say, okay, we're looking down, we're looking from above, we're looking down on a hill, maybe. And it's a hill that the further you get away, the steeper it is, and so the further you get away, the more force, the gravitational sort of, rolling force there is away from the origin. Something like that. Okay? Now, the other physical metaphor that I want you all to keep in mind, and by the way, both are important. You can't just pick one. Both are going to be important. What if this represented the flows of fluids? Can a fluid do this? Can a fluid flow like that? That'd be kind of a weird situation for fluid to flow like that, but a fluid can flow like this, where you have lots of fluid flowing out at the edges and only a little bit of fluid flowing out there. And so, for example, maybe you have a tank, right? And you're looking at the flow of fluid at the bottom of the tank. Maybe there's a layer of sludge at the bottom of the tank, perhaps. Right? And this is a tank that has a round base, and someone's poked holes around the bottom edge of the tank. And so there's water shooting out in every direction around the sides of this cylindrical tank, right? Well, the water shooting out of the edge is sucking water out near the bottom, and so the layer of sludge, the closer you are to the edge, the faster you're getting pulled along. The further you are away, the closer you are to the center, the more you're not really feeling that sort of pulling from those holes closer to the bottom. So something like that, maybe, yeah.
So then, like, in that case, would be this cross section. In that picture, it kind of makes me
Yeah, this picture would be a representation of, at the very bottom of the tank, how are fluids flowing. I mean, the thing is, if you're at the very bottom of the tank, the fluid can't be flowing down, and it can't be flowing up exactly, right? So it's going to be flowing horizontally, and with the water being pulled, toward the edges, it's going to be flowing faster near the edge and slower away from the edge. Yeah. It's just a metaphor. So let me say again, both of these metaphors are going to be important. We're going to do some pretty wild things with vector fields and different kinds of integrals of vector fields, and how to understand and visualize these things. It's very important to be able to understand them in terms of forces. To be able to look at a vector field and say, okay, thinking of this vector field as representing forces, then the sophisticated mathematical objects from Chapter 6 and late Chapter 5 that we're going to get to momentarily, I can interpret in a certain way as relates to thinking of this, in the context of forces. But then likewise, it's going to be very important to be able to look at a vector field and think, okay, thinking of this as fluids, thinking of this as a fluid that's flowing, the mathematical object of wherever it is, Chapter 6, Chapter 5, thinking of the fluid, thinking of the vector field as representing flows of fluids, the mathematical object is represented by, and again, there's going to be an interpretation. So both of those contexts really are important. So again, please don't just pick one. We're going to need both. Let's see. I skipped. Here we go. So going to this example now. What does this vector field look like given a point x comma y? The associated vector, negative y comma x. So what am I going to do about this? This is not exactly the position vector of the point that I'm at. It's not a constant. So one thing, you could do is just kind of point plot. You can take just a bunch of points, x comma y, and plug it and see what you get. And then at that point, you draw that vector. Just plot a bunch of these points, and you kind of get a picture of what this looks like. There's a convenient way to take advantage of an algebraic good fortune, though, here. And this does not always happen. But notice that this vector is always orthogonal to the position vector of the point. Right? So the dot product's always 0. And furthermore, these two vectors, the position vector and the field vector, always have the same magnitude. They have the same magnitude and they're orthogonal. And it's not hard to persuade you, having made that observation, that it looks like this. And I didn't draw this very well, but for this point, take the position vector for that point. The field vector has the same magnitude, which I did not draw well, and it's orthogonal. It's not hard to persuade yourself that that's what this looks like. And now again, you can think of this as, if you think of this as fluids, it's pretty easy to persuade yourself how this is a fluid. Someone's got a pot and they've stirred the pot, right? This is a stirred fluid flowing around in circles. As forces, this would be a weird, gravity can't do that, right? But you could imagine some scenario where forces are pulling you around in little orbits of some sort. Okay, let's see here. I guess that's all I have for that. Yeah, okay. Bunch of exercises. Now why do we care about vector fields? Why do we care about vector fields in this course anyway? This is a new kind of problem that I want to consider. This is a new physics problem. I want to compute the amount of work that it takes to accomplish a certain task. Now, quick callback. Y'all remember from chapter 1, right? One of the very first things that we did with vectors is we computed work. And y'all remember, high school physics, work is force times distance. Again, if you haven't had a high school physics course, no sweat. Work is just, it's energy. How much energy does it take to accomplish a certain task? Right? I've got a heavy box. It's sitting there. I need to move it over there. It's up a ways and over in that direction. That box is heavy. I got to move it a substantial distance, and there's a force involved. And how am I going to compute how much work it takes? How much energy? How much gas am I going to burn in my car? What have you to get the task accomplished? So that's called work. Okay, and the big conclusion that we had was that the old high school formula of force times distance was expressed awkwardly. I guess it's appropriate to the high school context, but now that we're in Math 212 and we know what dot products are, it's much easier to recognize that if you're displacing by a certain displacement vector, and over that displacement, if you were exerting a certain force, it was much easier to just write work is equal to force dot displacement. Right? We're very proud of ourselves because this recognizes the fact that the force and the displacement are not scalars. So we're not treating them as scalars. We're recognizing they are vectors. We're treating them as vectors, and this vector operation of dot product is exactly what we need in that situation. Okay. So what we're going to consider here is a yet further variation where we're going to start here and we're going to end there, but we're not going to follow that path. We're not just going to displace directly straight line from A to B. Rather, instead, we're going to follow a curved path. How does that change things? Something we're going to have to worry about. Worse, we're going to recognize that the force that we're applying might not be constant. It might not be the same everywhere. So, for example, at this point, the force is that, whereas at this point over here, the force is different. And had I ventured on my path over to there, the force is completely different there as well. And at that point, it's totally different. Right, so there's a temptation to say, well, look, you're just going to take all your little displacements and the dot product with the force, but the force keeps changing. So we have a non-constant force. We have a non-straight displacement. We still want to compute work, but it's just that I can't use the old formula because things aren't... We have a problem with non-constancy. So let me point out, that's a problem that we've had in every integral that we've talked about so far in this course. Every integral that we've written down, kind of the problem was that something wasn't constant. So for example, suppose I want to compute the amount of mass in a two-dimensional sheet where, density is a function of position. Well, the fact that density is not constant is the problem. If density was constant, I'd say, mass per unit area, just multiply by area. Boom. I don't need an integral. Ditto with computing masses on solids. Ditto with computing masses on curves in space, etc. The problem was that I had to break it up into little pieces because it was only on each little piece that the things that otherwise were not constant could be treated as constants. Okay. So that's really the problem we're dealing with here. We have some things that aren't constant. Okay, fine. Let's break it up into little pieces, and this great big curve that I have, there's my whole curve that, back there is where my starting point was, and over here is where my ending point is. But focusing our attention on just one little piece of curve. Teeny tiny little piece of curve. Maybe the problem will be simpler. And it is if you think about it. teeny tiny little piece of curve is approximately straight. It's not exactly straight, but it's really close to straight, and so I can view that vector as representing my displacement. Now the force that's being exerted, and by the way, there's a little awkwardness with minus signs here, but if the force that I'm experiencing is like this, like the gravity that the pen is experiencing here, right? It's a vector kind of pointing down. Well, yeah, but I'm exerting force up, right? I'm pushing the pen upward to keep it from falling downward. So I am applying to this pen a force that's the exact negative of the force that gravity is applying. Right? That's the force that I'm applying. The force on me, the wind that's blowing in my face that's trying to bowl me over as I walk along this path or whatever it is. The force that's being exerted on me is like that. I have to exert the negative force to oppose it. So, okay, on this little piece of curve, then, here's the story. On that one little piece of curve, it's approximately straight, and it's an itty bitty little short piece of curve, so the force is approximately constant. In other words, it's approximately the same force here all the way along. Try to do a better job than that. Approximately the same force all the way along that little piece of curve. We're back to chapter 1. We have a straight line displacement. We have a constant force. Close enough. And so work is equal to force dot displacement. Here we go. Work is equal to force dot displacement. So note the force is a vector. The displacement is a vector. That's a dot product. That's what I'm adding up over each little piece of the curve. Here's my entire curve. This is just computing the amount of work on one little piece of the curve. I have to add up over the entire curve to get the grand total amount of work. Right? And combining these together, we're adding up all the little pieces of work. Work is force dot displacement. Don't forget the minus sign. Right, the little minus sign in there is observation of the fact that I'm being opposed. And I have to apply a force that opposes the work that's being applied to me. And here you go. Here we have a construction that will allow me to compute work. Now let's take a moment to consider this little expression here. It's a limit of a sum. Gosh, that looks a lot like a Riemann sum. It looks a lot like a Riemann sum. Now, what's different is that's not a scalar quantity. That's not little f. That's not a real value function. Like every other integral that we've ever seen, this has been a real value function. And in every other integral we've seen, that's been a size, a scalar. Right? The differential here is now not a size. This is a vector. It's a displacement. So but it's still kind of a differential. It's a size and a direction as opposed to just a size. But come on, the expression is really got a lot in common with Riemann sums. It looks a lot like a Riemann sum. It's just a little different. Okay. There's a dot product of the vector integrand and the vector differential instead of a plain old times with the scalar integrand and the scalar differential. So anyway, we have to recognize it's a little bit different kind of an integral. It's really not exactly like any of the Riemann sums we've seen before, but it's got an awful lot in common in the sort of, chop it up, add it up kind of point of view. Okay, so new definition. Right? This is a new construction. This expression here, chop it up, add it up on the question of work being exerted to compute, or to move a mass over a particular curve. On each little piece, force dot displacement, add up over all the pieces. So again, the notation's super plausible. dx, our shorthand for delta x. We've used this notation before, by the way, dx vector. This is a vector that represents displacement. It's a displacement differential. Right? It's the differential of changing position. The integrand. Well, just write the vector field. Right? The thing that we're dotting, the thing that we're multiplying by the differential. Just write that down. And everything else in the notation is, again, highly familiar. Using an integral symbol. Well, yeah, of course. We're doing an addition. We're doing an addition over a curve. There's one index because it's a one-dimensional curve. Whatever that domain is, write that down as a subscript. It's extremely familiar notation. So we're going to make this our definition of a well, gosh, what are we going to call this? It's a line integral, isn't it? I mean, we started off with a curve. We're doing a chop it up, add it up on a curve in space. We've already agreed that we're calling that a line integral. It's just that previously, when we did chop it up, add it up on a curve, we were chopping up and adding up scalar quantities, and so I put this prefix in there. I call it a scalar line integral. Here, we're doing chop it up, add it up, but on each little piece, we're looking at vector quantities. And so, correspondingly, I like to call this a vector line integral. Now, that's my terminology, right? Common terminology, you just call this a line integral. Again, the context will always make it clear. If you talk about a line integral of a vector field, well, of course you mean a line integral of the vector field dot the displacement vector, of course, because that's the other construction doesn't make any sense for a vector integrand. So you can argue that this prefix of calling it a vector line integral is unnecessary, but it just kind of makes me uncomfortable to give the same name to what are two different constructions. So I like to call this a vector line integral, and the thing that we talked about, computing mass of a bent rod or computing how much snow I had to shovel that one day, scalar line integral. Scalar quantities. Okay. All right, so vector line integral. Again, how are we going to compute these things? Here's our situation. Got a curve. This is our third time down this particular road. We've got a curve. It's a curve in R2. I don't like this as a domain. The reason I don't like it is because it's dimensionally awkward. It's a one-dimensional thing in a two-dimensional world, possibly even three, right? So it's dimensionally weird. Let's view this as an image of something more desirable and do a pullback. I know how to view curves as images. These are parameterizations. It's the same parameterization that we were doing back when we were talking about scalar line integrals. The pullback domain, again, is just going to be an interval on the t-axis, interval from some point A to some point B. Same story. Again, it's real easy to relate the things in question. So we're looking at this vector here, dx. There's our position differential, or dx vector. We've got this scalar quantity here, dt. Now, in the context of scalar line integrals, we were interested in a size compared to a size. And so, I wonder about how big is that? How big is that? What's the relationship between the sizes of these things? And we ended up looking for this thing called the stretching factor. The stretching factor was really just a kind of a convenient way of getting our hands on how can we write this thing. What we needed to know was the size of these pieces. Okay, now here's our current situation. I want to know not the size of this piece. I want to know that vector. I want to know the dx vector itself, not the size of it. The size is not good enough. I need to know both the size and the direction. So I need the vector dx itself. Well, good news, I already have a formula for the dx vector. We computed this when we were doing scalar line integrals. It's kind of counterintuitive if you think about it, but the way we computed scalar differentials was first by computing that dx vector differential, and then by taking the magnitude of it. So let's say it a different way. What we did previously was we found both a direction and a magnitude, and then we threw away the magnitude, leaving the direction. Sorry, I said it backwards. Sorry. Let me try it again. What we previously did is we found both a direction. I'm trying to avoid making a rude gesture. Finding a magnitude and a direction, and we threw away the direction, thus leaving the magnitude. Right? So magnitude and direction. But that's what we wanted. That's what we want now. So instead of throwing away the direction to get just the magnitude, we're going to keep the direction. In other words, just keep the dx vector that we computed 3 sections back. So look back into the section on scalar line integrals, and you'll notice that this formula is in there. The very first thing that we did was to compute the dx vector, and then we said, yeah, but we need size, so we then had to go further computing the magnitude of this, which was really just throwing away free information. We were throwing away the direction. All we're going to do now is just keep that direction. So we're done. It's weird to say, but I mean, it feels like we're doing less calculation here. And we kind of are. We're doing less calculation for a more sophisticated construction. It's very, very weird. Anyway, here it is. dx is just v dt. So it's real easy to do these pullbacks. You don't even have to compute magnitudes. If you have a vector line integral. Now, we've only seen one application, by the way. I'm going to interrupt myself. The only application that we have so far, why we would be interested in a line integral of a vector field, is the computation of work. So here we're thinking of F as representing forces, and we're moving along some curve at every point of which we're exerting some forces, and I want to add up over that entire curve the work that I'm doing each step along the way. All right, so if I want to compute one of those kinds of integrals, then plug in the parameterization. Force is a function of position. Okay, sure, but position's a function of time, so now force is a function of position. And our displacement differential, dx, yeah, velocity times time. Old news. It's like I didn't really have to do any effort at all. I mean, any calculational effort to get this formula at all. I already had these formulas that I needed. Okay, so let's do one. Let's see, do we have time to do one? Oh, no, we don't. We have 10 seconds, so then we're not going to make it. Okay, anyway, so we've done some good setup work. I'll remind y'all, we'll go through this calculation again on tomorrow, and we'll pick up here where we left off. Okay, see y'all later.